Good morning and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We're going to get straight to today's Mars report. I'll introduce to you the speakers for today's news conference. We have today Jennifer Trosper. She's the Mars Science Laboratory Mission Manager. She's with the Jet Propulsion Laboratory. Justin Mackey, he's an imaging scientist on the Mars Science Laboratory mission, also with JPL. John Grotzinger, the project scientist for the mission, and he's from the California Institute of Technology. Michael Malin, principal investigator for the Mars Descent Imager on MSL. He's with Malin Space Science Systems in San Diego. And Don Hassler, he's the RAD principal investigator with Southwest Research Institute in Boulder, Colorado. And we will begin with Jennifer.
Good morning. Well, we have some great news. Sol 2 has executed on the rover, and it executed flawlessly. So we accomplished the main things of getting our high-gain antenna session to work, and we have now confirmed that all of our antennas and all of our links on the rovers work perfectly. And I just want to congratulate Peter Eilot and his team, because there's been an enormous amount of effort to make sure that worked over the last 7 years, and they are sending us lots and lots of data. We got 100 megabits on the MRO AM pass yesterday, so fantastic work by the telecom team, and also fantastic work by Odyssey and MRO orbiters and the DSN, who's been supporting us getting all that data back. So we feel very confident that we have lots of data capacity now with all of these links, and that was one of the major objectives of this first part of the mission. So that's fantastic. We also, you'll note that the rover model now has the RSM deployed, and that's consistent with what the actual rover on Mars looks like. And it's pointing here away from the sun, and in a minute I'll talk a little bit about the anti-sun image that we took. And then I also wanted to talk about the fact that we've cleared the REMS anomaly. So we had some issues with REMS. We understand the problem. It actually was related to the management of REMS parameters in their non-volatile memory. The engineer, Anthony Scuderi, has been working with them. They understand the problem, and we're on the path to collecting. And we actually got data down that shows the instrument is completely healthy.
Jennifer,
So
I'm going to just ask you to explain REMS, the acronym, and for those who don't know what the REMS instrument is.
oh, okay, the REMS instrument is the weather instrument that we have on the rover. So that's the instrument that we had an anomaly with yesterday. And so that instrument is now healthy. We got the data down to show that it's completely healthy, and we'll be operating that not on Sol 3 tomorrow, but on Sol 4. So all good news. As far as the other systems on the rover, the power system, very healthy. The radioisotope thermoelectric generator, RTG, that's generating power for us is a higher power, about 115 watts, and we've been using a conservative 105 watt predict. So we have more power than we expected, and that's gonna be fantastic for being able to keep the rover awake longer. We also have some thermal data indicating that it's a little bit warmer than what our predicts say, and we're still looking at why that is. In general, it could be that the environmental models are a little bit different for Gale. It could be that our actual models of the rover are a little bit different. So we're investigating that. There's actually not a significant issue with that, except for potentially we would have different constraints on time of day when we would operate the instruments. An actual huge advantage of that is that in warming up actuators to do things like drive and move the arm, we'll have less energy that we have to use to do that. So we're looking at the thermal situation. As far as our plans for the next Sol, so we're planning Sol 3 right now. There's a lot of folks over there getting the plans and sequences together for the next Sol. And very exciting, now that the mast is deployed, we're going to do the Mastcam 360 full color panorama, and I see the folks who've been working on that for several months smiling back there and excited that it's going to run on Sol 3 just like we planned, so there are going to be some amazing images from that. The other thing that we're doing on Sol 3 is we're getting ready for the flight software transition. So there have been a couple folks who've been working for over a year on how we transition from the R9 flight software to the R10 flight software. They've generated hundreds of files with thousands of commands that we have to execute over the 4 sols of flight software transition, and we're going to uplink those on the high gain antenna the morning of Sol 3 so that they're all on board and ready to go for the Sol 5 to 9 flight software transition. So it's very exciting. We wanted to get this thing started on Sol 5 to make sure we got to the new software. One of the other just issues, not a significant issue that we're looking at, but you can see where the high gain antenna is here. And as Earth sets, there's a little bit of an occlusion between the high gain pointing through the low gain antenna at Earth. And so we don't actually have horizon to horizon coverage of the high gain antenna. So today we're going to operate the high gain antenna all the way through Earth set so we can characterize what the real occlusion is with the low gain antenna so that our future high gain antenna windows can be consistent with what we believe the capability of that to be. So with that, I'd like to introduce my colleague to the left. We were just talking, we've been working together for 16 years. We were both very young and not that smart on Mars Pathfinder, and you can make an assessment of where we've come, but Justin Mackey actually built and is operating the HAZ cams and the nav cams on MSL. And if you'll bring up the first image here, this is the anti-sun image that shows that the go ahead and bring up the first image. I think it's the image. It's the first image in Justin's package, and it's the image. If you look up here at the rover that we took, there it is. So I have the RSM in the position of where it was pointing when we took this image. So you can see it's pointing down here. You can see the shadow of the arm in the image, and you can also see that the mast is deployed, which is excellent. That's what we're looking for. And the reason we take this image is we actually did a sun find to update and make sure that our understanding of our azimuth angle was correct. And then we take the anti-sun image to make sure that it's 180 degrees off of what the shadow is lined up with where the sun is on the other side. That did update our azimuth about a degree from what we had from gyro compassing. But since the high gain antenna session worked great yesterday, it'll probably just work even better today based on that degree of update of our azimuth. So Justin Mackey, again, is the owner of the cameras who took this image, so I'm now going to pass it off to him to talk about that and the other images that he took yesterday.
Okay, thanks, Jennifer. Well, this is our first image from the NavCam of Mars on MSL, so it's notable in that sense. Not only was it used to check out the rover's attitude and positioning system, which, as you can see, it did very well. The idea of the anti-sun image is that the shadow should be in the center of the image. And it may look a little off-center, but the reason that it's slightly off-center is because we use the left nav cam to acquire that image. So if you look on the left side, you can see that that's in the center of the image, and we verified that. It's a great shot because it does show Mars. You can see in the lower left portion of the image, you can see the robotic arm. There's a cover there with the Curiosity logo on there. There's also a what's called an augmented reality tag there. That's that little pixelated rover that's kind of near the center of the image. And I'm told that this is going to be active once the rover starts moving. You'll be able to take your smartphone and point it at that tag, and it'll take you to a website of interest related to the rover operations. And the other thing I'm going to mention is the lower right side of the image there you can see one of the rover's wheels. And when this came down overnight, we were happy to see that the rover is relatively dust-free. There was some concern that we did kick up a lot of dust during landing, so this image sort of shows that it really isn't that bad. We do see a thin coating of dust, but nothing too bad. So the next graphic, just to give you a quick overview, shows the nav cams you can see there. It's a stereo pair of cameras, and the field of view is shown there in the image. It's a 45 degree by 45 degree field of view, and the cameras are designed to provide navigation and planning assistance. So we do 360 degree panoramas and use those stereo images to do drive planning and science instrument targeting. So the cameras were built here at JPL. They are copies of the MER nav cams, which they're identical. We call that a build-to-print development. So we take the same design that we used on the last mission, we built them for MSL, and they're working very nicely, as that image showed. We checked out the cameras with that image, and we're very happy. All the exposure times are as expected, and we're going to go ahead and go to the next graphic. After we did that image, we went ahead and acquired a 360 degree panorama. And so this graphic shows the thumbnail images from that panorama, which are these little 64 by 64 pixel images that take up very little data volume. So we downlink those over the UHF pass tonight, put together this mosaic. And I should mention that these mosaics are being also generated here at JPL by the Multi-Mission Image Processing Lab. So we're going to be downlinking the full frame versions, the full resolution versions of these images over the next day or two. The next graphic shows what we call a polar projection. We also took a panorama of the deck. We call that the deck pan. And we took this to document the state of the deck after landing. It's still a low resolution because this is also generated from thumbnail images. But you can see the rover there. North is up in that graphic. The RTG is on the left side. The front of the rover is on the right side. And you can see the shadow of the RSM there pointing to the right. And if you look closely, you can see the wheels there on the bottom side of the rover there, and that's just sort of a precursor of things to come. We're going to get the full resolution versions of those images down, and we're looking forward to getting those. So the next slide shows the first two full-frame images that we've downlinked from our 360-degree NavCam panorama. This is just a great shot. It's pointed to the north. It's a mosaic. We call it a 2x1 mosaic. You can see in the near field the scour marks that the descent engines made on the surface, which kicked up some of that dust that we saw in those HazCam images on landing day. And as you go out towards the horizon, and near the middle of the image, it's sort of sloping downhill, and then there's a little drop off there about the middle of the image. It's a little hard to tell in the graphic, but beyond that, you go all the way out to the horizon, you can see the north crater rim of Gale Crater. So this image is just fantastic, especially for those of us that worked on developing these cameras. And we're very excited to see the system working. And based on what we've gotten in the last 12 hours, we've declared the NavCams commissioned and ready for use. And with that, I will turn it over to John to talk a little bit more about what's in the image.
Right. Thanks, Justin. Okay, so if we can go ahead to the next one there, you'll see the same image that Justin was just talking about. And we are looking to the north, and so that's the rim of Gale Crater, and that's the part of the rim of the crater which is lowest in elevation, facing the northern lowlands of Mars. So it's been very deeply dissected, and the thing that really struck the science team about this image, that you would really be forgiven for thinking that NASA was trying to pull a fast one on you, and we actually put a rover out in the Mojave Desert and took a picture, a little LA smog coming in there. And so the thing that's amazing about this is, to a certain extent, the first impression that you get is how Earth-like this seems, looking at that landscape. And maybe one of the reasons behind it is that you're also looking in the same direction that this alluvial fan is coming from. So all the sedimentary materials, all the part, not necessarily the things you're looking at, that's all TBD, but more distally, what we can really confirm in terms of looking at the high-rise images is that all those materials are derived from erosion of those mountains there. That's the source region for this material. So it's really kind of fantastic to look out across there and see something that has really attracted people to particular parts of Mars for years, wondering what would it look like if you landed on a landscape where there was an alluvial fan that was created by water. So there you're looking towards the watershed that delivered those materials. So in the middle ground, you can see some dark-looking ridgy features. Those are scarps, probably 1 meter, 2 meters, 3 meters in height. We have no idea what those really are. They're related to the bedrock that we see exposed. You're looking toward the high thermal inertia area over there. And then in the immediate foreground, you see this little low that Justin mentioned. So at a very low slope, a degree or two away from the rover into that depression there, we don't yet know geomorphologically what that means, but there's some kind of a low there. And then right in the foreground is something that's particularly interesting. Justin mentioned these are the thruster impingement excavation areas. And what's cool about this is that we got some free trenching. On MER, we often discussed, how we would take the wheel and scuff and dig, and we did. And, people like Rob Sullivan put a lot of effort into that, and we'll do that with this rover Curiosity. But here we get a freebie right off the bat. So if we zoom in, what's really cool about this, we're going to zoom into the mark on the side. And we estimate right now, as just chatting with Justin about, we're going to guess that this is approximately a half a meter in width there. What you see beneath the soil is bedrock. And for those of you that may remember the Phoenix landing, you excavated, and what were you looking for with Phoenix? You're looking for ice. And so what we're really looking for here is a diversity of materials, and so we see our first glimpse of bedrock. And so apparently there is a harder, rockier material beneath this veneer of gravel and pebbles, and obviously there's some impact ejecta in there as well. And so we're already getting a glimpse into the subsurface here. So, for example, when we turn the DAN instrument on for its checkout, an intermission will drive along, and we'll want to know what's in the subsurface, and here we've already got an exploration hole drilled for us. So when we interpret that data, we actually have some understanding of the depth to bedrock for understanding what the subsurface is that we've never done before with a rover mission. So with that, just a little teaser as to what's to come in the future, and I'm going to turn it over to Mike to show you some really cool stuff.
Thank you, John. I've actually two things I'm going to share with you today. The first is not really directly related to my role on MSL, but to my role in the MRO project. I'm the team leader for the imaging system on MRO, and one of my team members from my company was targeting MRO up here as part of her duties, and she brought to my attention the first thing I'm going to show you. I need to set the stage because it's going to come on the screen and then it's going to flash off after a couple of seconds. What you're going to see is a picture that we took on August 1st of the landing area, and obviously the lander and its other pieces are not in that image. And then the second image you'll see, it'll come up in 2 seconds later, is going to be the image we took on the 7th at the same time that HiRise was taking the picture that you've seen. I think there are pictures in the back of the room of that. And so we rode along with the HiRise. The context camera is a much lower resolution camera. It's 1/20th the resolution of HiRise, so we 20 times poorer. So we get 6 meter per pixel, take the image, 5 meters when we map project it so that we can compare image to image. But we also cover 50 times more area than HiRise does. Our swath width is typically 30 kilometers wide, and this particular image had a 42 kilometer width because we were looking sideways at the surface. And the entire image is like 275 kilometers long. So we cover a huge section of Mars when we take these images. Lilia was looking at the after image, and she found something a little odd. So I'll draw your attention when the pictures come up. Look to the right side, sort of down range from the area where the other pieces of the vehicle fell. So if we can have the first graphic, it'll basically flash between, that's the after, there's the before, there is the after, there is the before, and look over at the right by that little mesa, and there's just to the upper left of that mesa, you see these little black things flicking on and off. Okay, so Lilia blew that up. And if we go to the next slide, this will also be another flickering image, no, and then you see 6 spots. What are those 6 spots? Well, Lilia knew enough to go asking people. Ken Edgett came in and he saw this on the screen from the door of our room and said, "What's that?" Because it's very obvious to people who know Mars. Lilia and Ken know Mars very well, and very obvious to people who studied of Gale that these were different. And basically, those are the 6 entry ballast masses, EBMs, I guess they're called. They're 25 kilogram tungsten slugs about this big. They hit the surface and they disturb the surface, And these particular things are about 12 kilometers downrange from the lander. They have about a 1 kilometer dispersal. And these were what was thrown off just before the straighten up and fly right phase, just before parachute came out. They followed their separate path to the surface, and that's where they hit. So it was a great find by Lilia, and we're all very pleased that it worked. And the EDL guys were very excited to see these, because this is another test of all the modeling they've done for EDL. This tells them how inert objects that aren't doing any activity come through the atmosphere and fall. There are other pieces that we will look once MRO is allowed to turn its payload back on. We will be able to do that test, go look for these other large features. So that's my first story. We were all very excited about that yesterday. Next slide is going to show you next thing is going to show you an animation. This is going to be the first 25 seconds of the video in thumbnail form. You're inside the vehicle, inside the aeroshell shell, so you didn't see anything, and then the heat shield fell apart. So the first part of that, you were in the dark because there was no light inside the aeroshell, and then it popped off, and you saw it moving away. This is, again, a thumbnail resolution video, but it gives you an idea of sort of the kind of action we're going to see in the near future. And that was 6 seconds of dark at the beginning inside. That all was taken about 2.5 minutes before we landed. The next slide is going to show you something you've seen before. This is the thumbnail that I showed a couple of days ago of the heat shield at a distance of about 15 meters. The heat shield is about 4.5 meters across. And the next slide shows you the full resolution system came back. And you've been hearing us keep saying, well, just wait till you see the good stuff. Well, this is the good stuff came down, and it's quite spectacular. You can actually see the stitching in the thermal blanket. You can see there's wiring in there for the medley experiment. And so eventually we hope to have that same animation I just showed you at this resolution. So I was actually going to do a couple of these thumbnail, then full resolution ones, but don't have the time for that. So the next slide is going to show you a high resolution view of the vehicle sitting on the ground. This is, the camera is 0.7 of a meter off the ground, and it's looking down. This is the view the camera will have from now on. It turns out it's about 0.9 of a meter wide, so it's about a yard wide. And once you do this map projection to get it out, get the distortion out of the lens, and you can see a pebble there that's 5 centimeters across. You can see most of the material in there is smaller than that. And so this is the gravel that's covering the surface. We actually are seeing some color differences in the material, but I don't believe them because I think the way the Bayer filter is reacting to that is being spoofed by the illumination conditions, so that something that's darker is looking colored. But Tim Parker has been working on a super res, because we took hundreds of this image, and he's been putting them co-adding them together, and we're getting spectacular spatial resolution out of that. This image is slightly out of focus because the camera's not in focus at the surface, but it's not as much out of focus as I thought it was going to be. So it's really nice. The next one, I think, is another flicker. Yes, this is a high-rise view. This is the gray one is the high-rise scale base map. The colored one is the MARDI taken from an altitude of about 170 meters, which is about 44 seconds before touchdown. And the field of view, what you're looking at there is about 215 by 150 meters. That little white box is the size of the rover, and it's located where we know from the closer images where we can match up rocks and things like that. We know that it's positioned where the rover is. And if you, it's very hard to show you at this scale, projectioning and things like that. You should look at the image that's going to be on the web. if you look at, there's a bunch of rocks and boulders in the upper left corner of that image. There's also some bed forms, aeolian bed forms in that crater to the lower left, sort of not the lowest left, but in the middle left there. There are all sorts of things. There's a very, very sharp little rock to the southwest of the rover by probably looks like 50 meters. But, I look at this and I say, well, I know, there are plenty of places we can go. There's some big question about, can we move the rover? Is it safe to move the rover? There's nothing around it. So it's safe to move the rover. There's nothing under it because we do have an image closer in as well. And so today's presentation for Marty was basically to fulfill the promise. We said, if you wait a little while, we'll have slightly better pictures. They're more than slightly better, and I think they show you that the Marty took some really good images on the way down. With that, I'm going to hand it over to Don.
Thank you, Mike. Well, it's really tough to compete with these fantastic images. But I'm going to report a snapshot of the first observations we have of the radiation environment on the surface of another planet, which in itself I think is quite remarkable. Interestingly enough, yesterday was the 100-year anniversary of the discovery of galactic cosmic rays on Earth by Victor Hess with his hot air balloon in eastern Germany. And exactly 100 years later, yesterday, we make the first measurements or characterize the first measurements of galactic cosmic rays and the rest of the radiation spectrum from the surface of Mars. So if we have the next slide, this shows basically zooming in on the top deck of the rover, showing where the RAD window is. So the Radiation Assessment Detector, or RAD, field of view is defined for the charged particle channel by this window, and that points towards the zenith. And so we characterize and measure charged particle radiation coming in from the atmosphere, as well as neutral particle radiation, neutrons and gamma rays. And we've learned a lot since in the last 100 years, since the measurements of Victor Hess. We know that, if you'll show the next slide, that the two types of radiation in space, the galactic cosmic rays and solar energetic particles, are driven in a large part by the sun. They go with the solar cycle. And it's actually a very interesting time because the entire nominal mission surface operations will be right around solar maximum. You can see the data in white and the prediction of the solar cycle in red. So we'll have an opportunity to really get a good characterization of both the galactic cosmic ray background, which is what Victor Hess measured 100 years ago, but also the solar energetic particles as they occur in solar particle events as a result of flares or solar storms on the sun. So if you take a look at this profile, this is basically sunspot number as a function of the solar cycle. Galactic cosmic rays vary on an 11-year cycle. Solar energetic particles are episodic. They happen on a scale of hours to days, and they can be very intense. The first measurements we had yesterday, the sun was very quiet in the location of Mars. So the measurements we have are pretty much primarily galactic cosmic rays. But if you show the next slide, this is really just a snapshot of pretty close to the raw data that we observed with RAD from the surface. So there's a couple of things to note. This was a 3.5-hour observation with about 1 minute time resolution, or one observation, 1 frame per minute of data storage. And this is really a plot of dose rate in arbitrary units because we haven't, well, first of all, the mast hadn't been deployed yet. So the mast was partially obstructing our field of view. Secondly, we haven't corrected for the RTG background, nor have we done a correction for the silicon in our plastic detectors. We have 2 different types of detectors on RAD. So these are really arbitrary units, but we have put, just for reference, the average dose rate that we observed during cruise. We had a little over 7 months of observations during cruise to characterize RAD and get a very good baseline in deep space. And now we are starting to take our measurements on the surface to characterize the radiation environment on the surface. So although this is a quiet time on the surface of Mars, there's really not a large contribution from solar energetic particles. You can see that the spikes in those in that plot are really individual heavy ion hits on the detectors. And it's actually the contribution from these heavy ions that are the biggest effect for biological organisms, whether it be microbial life on Mars or astronauts on future missions to Mars. And so what we will achieve with RAD over the next days, months, and years will be to characterize and accumulate the statistics, and also to gather energy spectra of each of these heavy ion events. Basically, we record, as I mentioned, we record the spectra of 26 different charged particles. So we're going to accumulate spectra, energy spectra from each one of these 26 different charged particles, so that we can understand and characterize their contribution to the radiation dose on the surface, as well as the contribution from neutrons. So this is really just a snapshot, but we do see the exciting elements of what we're going to be collecting and accumulating over the next months and years as we continue on with our nominal mission. So stay tuned for future results. Thank you.
All right, thank you. We're going to begin with questions here at the Jet Propulsion Laboratory, and then we will take some questions by the phone lines as well. And I'll start with Eric Hand. I saw that hand go up first. Let's just wait for a microphone to come over to you.
Thanks. Yeah, Eric Hand with Nature. I guess my question is for John. I wonder if we can bring up that image of the close-up, the half-meter sort of scale with the trenching in the trench, but from the retro rockets. Is that something we can bring up?
Can we bring that up? It'll just take them a
Okay.
second.
And I guess my question is, I don't know if I'm seeing things, but it seemed like there might be some sort of lineament there, and maybe even that's echoed at the top of the trench. I wonder if you have any thoughts on what that could be. All I'm thinking of is when Opportunity recently discovered that gypsum vein. So I'm wondering if already you can speculate on what could create a linear feature like that. Thanks.
I guess, sure, why not? I mean, that's an entirely reasonable suggestion, and it's something that the team was talking about, and I think we should just wait to get the mass cam data down to go further with that one. But yeah, I mean, it's a reasonable idea. What? That there could be fractures filled with some cementing material. Yeah.
Take one more question here, and then I will go to a question on the phone line next.
Hello, Olivier Sanguy, enjoyspace.com from France. I would like to speak about the temperature and the radiations. You said that the temperature was a bit higher than expected. Are you today completely comfortable with the condition on Mars about the rover, or there might be a problem, for example, with winter, etc.?
Yeah, I'll start, and then Dan, if you want to add anything, you can. As far as the rover itself, we don't have any concerns about the temperature being a little higher. In fact, normally when we land on Mars, we update our thermal models and predictions in the model of the rover to be consistent with what we see. So that's part of the process. We're taking a lot of telemetry. We actually woke up several times overnight last night to get telemetry points all through the night. And what we'll do with those is we'll update our models. They may put different constraints, but not significant constraints that we didn't expect. Maybe we would have, if things get too warm, we might have a shorter operating time before we had to let something like the cameras, for example, cool down. But we're still working on that. In fact, though, the higher temperatures are generally fantastic for us, because the real issue we struggle with is how much energy we have to use to heat the actuators to drive and use the arm. And this is good news on that front.
I think from an instrument point of view, all of these temperatures are within the operating range of our instruments. So I think it's interesting, but all the models typically have a variation, and I think we're within that.
And the radiation from the rover itself?
The RTG background is a fraction of the measurement, the radiation we observe from space.
Okay, let's go next to Ken Cheng, New York Times. He's on the phone line. Go ahead.
Hi, this is for Dr. Gottsinger. The bedrock that you see, would that be part of the original crater floor or just part of the rocks that formed later?
Ken, I think if I heard it correctly, you're asking if that's the floor of the crater or some later bedrock.
Yes.
Yeah. I think given the elevation and the projection of the geometry of the rim of the crater, it would be pretty high up to be the floor of the crater. So, you know, with lots of caveats, I guess our initial first guess is that it could potentially be, you know, a rock unit, and I want to put rock in quotations, you know, that formed sometime well after. And I put it in quotations because we don't know how hard it is yet. And there's, you know, people have different feelings about how hard a material needs to be before it's a rock. And we'll find out. So I'll just leave it at that. But it's probably not the floor of the crater.
So what's the difference between a rock and a hard place?
Okay, I saw Emily Lockdwala's hand up. If you can bring the mic to her, and then we'll do one over here, and then another one from the phones. Go ahead, Emily.
Hi, Emily Lockdwala, the Planetary Society. I'm wondering, the rocket's excavated pretty deep, which means that the soil you're sitting on is pretty disturbed. I'm wondering if you want to sample that disturbed soil originally, or are you going to have to drive away to get to some more undisturbed soil before you start with the arm work?
Well, that's a great question, and I can say that's at the core of the team discussion right now, because there's obviously an opportunity there, and the question is, you know, what if we would use the instruments there? You know, we have this thing called intermission that we don't have to drive anywhere if we don't want to. You know, driving's an option there. And as far as the contamination goes, you know, as far as the hydrazine and potential combustion products that are related to it, we've done a lot of studies. In particular, Ira Katz here at JPL has really followed up on that. And I think most of us have a reasonable level of confidence now. We don't have to worry too much about it, that within a sol or two, even for the SAM instrument, it doesn't pose too much of any kind of a risk, even with regard to interpretation of science data. So it's definitely, it's a bird in the hand right there. And I think we have to evaluate it very carefully and think about what we might do there.
Okay, actually, we're going to take one on the phone line, and then I'll come back to you, Leo. So go ahead on the phone, please.
Hi, Steve Cowling from NASAWatch.com. Question with regards to the time lag with releasing images. JPL's been pretty darn fast in releasing Cassini images raw and the twin rover images. But I guess the question is, you've got a yard tag on there. I mean, you guys are really pushing the envelope of immediacy. But even though the rover can't see small stuff, it can see larger stuff. And having walked around in places like Devon Island myself, things of a biological origin jump out at you. Now, I'm not going to ask you if you're going to find stromatolites or banded iron formations or anything like that. But if you're going to release these images and something jumps up that is clearly anomalous, possibly of biological or something origin, will you withhold that image? Will you just put that image out there? And what is the process? I mean, does somebody sit there and screen these things and say, oops, that looks like it's not just natural? And do you have a process that you can actually, you know, release or put on the web that explains exactly how NASA will and JPL will handle that information?
You know, we're going to have to, you know, we'll just see how it goes. I would say that, you know, our policy right now is to release all the images, and they come out there, and if there's a stromatolite there, then, you know, if somebody wants to interpret it that way, they're welcome to it. Our feeling is generally that we're not really worried too much about what folks beyond the team might want to interpret in terms of features that we might see, because our approach to this is always going to be to take a very integrated look using all the instruments, think carefully about what we're doing, and then make a statement. So if there was ever anything as profound as what you're describing, we would take our time with it, no matter how much jumping up and down there might be in the background.
Okay, we're going next to Leo.
Leo Enright with Irish Television for Dr. Hassler. The first cosmic ray experiment on the moon was an Irish experiment built up by the Dublin Institute for Advanced Studies. So there's a lot of Irish interest in this cosmic ray detector, believe it or not. And I was wondering, I mean, even looking at the early data, obviously the data set will be very, very large at the end of it. What do you hope from it? And can you say even at this stage what it would be like for a man or a woman standing on the surface from what you've seen so far? What sort of radiation dosage?
Well, certainly there's a number of models which would predict what the level of radiation would be on the surface of Mars. But it's a complex environment. The atmosphere modifies the radiation spectra, and so does the surface. Characterizing the neutron environment on the surface is one of the most interesting questions, or the least constrained measurements from models. So those will be some of the most exciting measurements. But the RAD instrument is much more than just a simple dosimeter. The simple plot of dose as a function of time is really it's like a thumbnail from an image point of view. It's the energy spectra that'll be interesting, and it's the energy spectra as a function of time. And so to compare those spectra for each of the different particle types, and to be able to compare those back and fold those back into the transport models, I think is really our goal. And I think understanding the transport means that we can improve our modeling, and therefore feed that back in and fold that back in so that we can design the most effective shielding for astronauts when we send them to Mars in the future.
Okay, can we bring a mic up to the front here? And then we will go back to another one on the phone lines.
Todd Halverson of Florida Today and USA Today for John. The NavCam panorama is kind of your first look at the neighborhood, if you will, and I was wondering what your immediate thoughts are about the scientific potential of the site you have landed on.
Oh, I think it's incredibly high. I mean, everything that we see there suggests a remarkable range of diversity, and I chose to single out the issue of the depth of the soil because, this is a question that Mars scientists have wondered about for a long time. And we have an instrument now, the DAN instrument, which can, reach down to a depth of 50 centimeters and look for hydrogen-bearing substances. And what that image just shows us right away is that it's not going to be ice. So we're good for planetary protection on that one, as promised. And instead, it looks like bedrock. And when that instrument was first built, I believe that the hope was that it might search for ice one day. And in the meantime, all these hydrated minerals were discovered on Mars. So in terms of applying it as a way of doing mineralogy in the subsurface that we're driving across, I think it's really exciting. And so the great thing about it is that we get an immediate calibration point of the depth of the soil. So as we drive away, the interpretation of the data will always involve interpreting a multi-layer system. And so we already have a hard data point on the depth to the hard rock. And if we choose to use our other science instruments there to see what's in there, we get compositional information as well. So that's just one example of how this really diverse payload can be used to figure out problems that have not been addressed before. And there's a ton of others out there as well we can see.
Okay, we're going to take the phone line next. It's Irene Klotz from Reuters. Please go ahead.
Thanks very much, Veronica. My question's for John Glotzinger. I was struck by your description of this early view of Gale Crater as bearing some resemblance to a view from Mojave Desert, and was wondering if you might give us a little geology class here and talk about what kind of conditions on Earth produce this sort of landscape.
That would take a long time. I think the short version of it is, let me try to paint the picture this way. When my first experience with Mars was when Spirit and Opportunity landed, and I think when Spirit landed, a lot of the folks that had worked on previous Mars missions had a feeling that this was a lot like Viking and Pathfinder, but when Opportunity landed, it looked completely different. And and those of us novices wondered at the time, gosh, is NASA making up this data? Because there's nothing that looks particularly extraordinary about this, until we saw all of these blueberries. And then you looked at it, and you saw the context for that, and you thought, nobody could make that up. It's just so weird. And now this time, with Curiosity, we land in something that actually looks very Mars-like, but it also looks Earth-like with those mountains in the background there, these deeply dissected pyramidal mountain ranges, and it just looks a lot like what you see out in the Mojave Desert. It's really cool. And so it kind of makes you feel at home. And without the geology lesson, I think that the great experience there is as we're looking at a place that feels really comfortable. And what's going to be interesting is going to be to find out all the ways that it's different.
Okay, we've got one here at the front of the room, and then I will go again to the phone lines, coming to you right there. There you go.
Kelly BD Sky and Telescope. Thanks to HiRise and Marty, I think we now know the landing site location to 8 or 10 decimal places. Can we please get, Jennifer, the time of the landing to 2 decimal places at some point, and maybe other entry events as possible?
Yes, in fact, I think I have the time on my phone here, and I can look it up. But and then we can tag up after, and you can tell me what other times you want. But you can go to another question.
Let's go to the next question, and when you have it, we'll come back and answer that one. So next, actually, we're going to MikeWallspace.com on the line. Go ahead.
Hi, this is for John. And yeah, I mean, I've asked you this before. It's just, so yeah, now that we know kind of where the ballast came down, where those craters are, is it really safe to say that they're far too far away for Curiosity to go and check out those new fresh impact craters? Is that just not possible?
Scientifically not possible.
Yeah, I think I think a lot of us hoped that those things would come down really close to where we landed, because as tungsten, it's fairly inert, and it makes a fresh impact crater that you could look in. So there'd be a lot of desire to do that. These things are really far away. They're sort of, as the crow flies, they're not that far away, but our obstacle is this dune field that we have no desire to drive across unless we have to. And other than that, they look like they've landed in a part of the mountain there that has mass flows that will be interesting in their own right, but they obscure the stratigraphy that we're after in terms of the target that we want to go to. So we would have to do an enormous U-turn around the dune field, and I just don't think it's going to be practical to do that.
Okay, let me get someone who has not yet asked a question. Go ahead, over here.
Thank you very much. I'm Fernando Correa from Tercer Milenio in Mexico. In my country, I'm an astronomer and study the space weather and present in TV to Coast. Congratulations for the space weather from Mars. The question is, in the Phoenix mission, NASA develops a software to watch the meteorological conditions in my computer. Will be something like that with Curiosity?
Well, the REMS experiment will provide weather, as in winds and temperatures and pressures, as well as UV radiation. We will also be measuring the space weather from the surface in terms of energetic particle space weather. And those will be available. I believe both REMS and RAD, we do have plans to broadcast. We only get the data down once a day, so it won't be real time. But there are plans to provide these in as close to real time as we can, at least certain summary data products.
Thank you very much. Congratulations again.
Thank you.
Okay, I'm going to start with some who have not yet asked back here, and then we'll make our way back up to the front.
Hi, Mark Kaufman of the Washington Post and National Geographic for Mike Malland. You had made some references to color that may or may not be there in the image. Could you walk us through that a little bit more in terms of what color might be actually observable and able to be photographed, or the extent to which Mars is the color that we're seeing right there?
Okay, this image has been processed just to make it bright enough for you to see. You can see that bright streak was like 8 times brighter than the shadow around it, and what you were getting was leakage of that light, smearing of that light into that dark area. it's very difficult to do what's known as photometry in a shadowed area like that. So I think any color information that I was seeing in there would be suspect. This image was sufficiently processed that I would not contend this is what Mars looks like. I personally am more interested in the rocks than the background fine materials. So I was interested in just showing you the morphology of what the surface looked like. This camera does have the Bayer color filter on it. That's the same way, it makes color the same way your cell phone camera makes color or your camcorder makes color. You have a black and white detector on which you put a filter that has red, green, and blue patches on it that exactly match up with the pixels of your camera. And then you use some interpolation techniques to average all those pixels together to make a red, green, and blue picture. That's been done to this. It was done to this image on the spacecraft. So our camera actually did that interpolation and then did the JPEG compression. JPEG compression almost always works not in red, green, blue space, but in a completely different mathematical color space, which is YCRCB, which is an old NTSC television colors code. That's when JPEG was developed and used that. So it's very difficult for me to give you a specific answer and say that color is right, that color is wrong. However, on the other cameras where we have calibration targets, we'll take images of the calibration targets, then we'll take images of Mars, and from that we can say, well, the calibration target, we know what those colors were, and we know under the same illumination, here we're seeing the surface of Mars, this is the information we're getting. So the mass cam in particular has multiple science filters as well as the Bayer pattern filter, and that will be how we derive our color information. This is not real good color.
Okay, let's go first to Jennifer. You have the answer for the question about the touchdown time.
Yes, we actually have directly from the flight software message that is sent to us from the vehicle. 2012, day of year 219, T05-1757, which is the UTC time, which is about 10:17 p.m. Pacific time, PDT, and you'll remember we didn't get the signal until 10:32 or so because of the one-way light time to Mars right now. Justin and I were also talking, we can get you the actual time of that first HazCam image, which was taken between 1 and 2 minutes after that. And yes, just the time again. Day of year 219, 05-1757 UTC.
Okay, another question here in the room at the back. Right there, thanks.
Hi, Hidemasu Moto from NHK TV Japan. This is a question for Don Hassler. What is the average level of radiation during the 8.5-month cruise from us to Mars? And what are the implications of those data set for the future prospective manned flight to Mars?
Well, we're still folding in the contributions from both the neutral particle measurements and the charged particles and separating out the background from the RTG. But from the just a little over 7 months of cruise data, we get a fraction, a few tenths of a sievert of dose equivalent, which is, it's if you assume an astronaut career dose is on the order of a sievert, that's it's a few tenths of that. So it's a significant contribution.
Okay, I think we have time for one more question. I'll take Alicia Chang.
Question for John. I was wondering if the robotic arm can reach out to touch the scour marks, and now that you've gotten a good look at the surroundings, whether there are any thoughts to stay in place initially or take a short drive after the health checkup?
Was the first part, how far does the arm reach out? Don't know. Don't know. Yeah. Justin's estimation is it's probably twice as far as we need, so that we'd have to move. And then the second part was, could we move if we wanted to?
for the initial science plan, whether the plan is to stay in place at first to sample the region around or to take a short drive?
It's wide open right now. The commissioning activity period that Jennifer is leading allows us the capability in what we call intermission to drive if we want to. And so certainly it would be an option to bump 2 meters forward so that we could drop the arm down there if that's what the science team wanted to do. Or any other option if we decide we want to drive, if we decide we do want to drive out of the area of contamination, where contamination means wind disturbance and see pristine materials, or if we want to go further beyond that, maybe go several tens of meters, all this is open right now. So we just, the great thing about it is that with the spacecraft being as healthy as it is and the capability that it has, all our options are open for science.
All right, we invite you to join us again tomorrow at 10 a.m. Pacific time again for another Mars report from the Jet Propulsion Laboratory in Pasadena, California. Thank you for joining us.